prefetta qua. Un annuncio tecnico. Volevo che tutti foste coscienti del fatto che c'è una traduzione simultanea. Basta scaricare una app, le istruzioni sono in un foglio che dovreste avere, si chiama Converso, questa app. Ecco, scaricando quella si può accedere alla traduzione simultanea, quindi siete pregati di usare gli auricolari, non il videovoce, e casomai tenere il telefonino, se non avete gli auricolari, attaccati all'orecchio. Scusa, una comunicazione tecnica questa. Naturalmente, se invece volete fare l'esercizio di sentire un fluido inglese, allora sentiamo in diretta direttamente il nostro speaker, anche perché le trasparenze sono scritte comunque. Quindi però Converso è un'app, è la prima volta che la proviamo, bisogna dire. Lo facciamo perché è una cosa un po' più economica che non chiamare un traduttore con una cabina, quindi è uno esperimento che facciamo tutti insieme, poi ci direte se funziona. Benvenuti a tutti al Gran Sasso Science Institute. È un piacere per me presentarvi oggi questo livello di oratore, Kip Thorne. Io ho qualche nota di presentazione, lo farò in inglese e quindi così vediamo se comincia a funzionare il sistema di traduzione simultaneo. Our speaker is Kip Stephen Thorne. Of course, everybody knows him. He's worldwide now because he was awarded the Nobel Prize in physics, along with Rainer Weiss and Barish, for decisive contributions to the LIGO detector and the observation of gravitational waves. Actually, I learned that his father was a chemist and that his mother was an economist. So you are particularly well placed here, Kip, as we are very interdisciplinary here, of course. And the Kip's mother was the first woman to receive a PhD in this discipline from the Iowa State University. Well, he got his bachelor degree from Caltech in 1962, and then the PhD degree from Princeton University in 1965 under the supervision of John Archibald Wheeler, which is, I think, known to most of you. And actually was one of the youngest full professor in the history of the California State University, I think in all over the United States at the age of 30. Of course, he's known for his contribution in gravitational physics and astrophysics. He's one of the world's leading experts in the astrophysical implications of Einstein general theory of relativity, black hole cosmology, wormholes and time travel, relativistic stars was all topics of his career. He also is very known for writing and editing books on topics like gravitational theory and high-energy astrophysics. Actually, in 1973, he co-authored the textbook Gravitation with Misner and Wheeler, that according to several is one of the great scientific books of all times and has inspired generations of students. Myself, let's say. In 1984, he published Black Holes and Time Warps, the Einstein's Outrageous Legacy, a book for non-scientists for which he received also numerous awards. And then, more recently, in 2014, published The Science of Interstellar, in which he explained the science behind the Christopher Nolan's film Interstellar, which also I think is widely known. Actually, we were speaking before that Kip invited me almost 20 years ago to give a seminar in Caltech, and it was one of my best memory I have of Caltech and of my career. So, ladies and gentlemen, Kip Thorne.
Thank you, Eugenio. Can you hear me in the back? Is this okay? 50 years ago, when I was just starting my career as a professor at Caltech, we thought that there might be what today I call the warped side of the universe. It's not a phrase we used then, but the idea was there then. By this, I mean objects and phenomena that are made from warped space and warped time, that is, distorted space and time, and instead of being made from matter like you and I. Examples that we speculated about were black holes, gravitational waves, the Big Bang birth of the universe, which involves quantized, quantum mechanical warped space and time, wormholes, and time travel. These were all in our speculations at that time, They were all basically speculative with a greater or lesser degree of confidence. What I'd like to do this evening is tell you what we have learned about this during the past 50 years. So in some sense, this is an overview of my career as a professor. I should say I retired from being a professor at Caltech 10 years ago to start a new career that is largely in collaborations with artists, musicians, and filmmakers at this interface with science. So this is, but I have continued to do some research, and so this continues on through my career and continuing research, even in this era when I'm enjoying collaborating with artists. Let me begin with black holes, and let me begin by a simple analogy. Black holes are made from warped space and warped time. As an example, a black hole is a black sphere that has a diameter that's far larger than its circumference. And you look at this, obviously the diameter is less than circumference, but I claim that it's actually larger, and I can explain that by this simple analogy. If you take a rubber sheet, say a child's trampoline, you put it up on high sticks or poles, and you then put a heavy rock in the center so that the rubber bends down like this. And if you then are an ant and you live on this rubber sheet, you're a blind ant, so you can't see what's happening, but you've studied here at this institute, and so you know that a good thing to do is to measure the geometry of your universe. And so you walk around and you measure the circumference, and then you set out to measure the diameter, and you walk. It's a very long distance around, and the diameter obviously is much larger than the circumference. And so there's how you can have a diameter much bigger than the circumference, because the space in which you live is warped. Precisely the same diagram describes a black hole. I just changed the labels. At the center, there's something called a singularity, which I will not talk about, but you can ask about it in the question period at the end if you wish. What we're now looking at is the geometry of an equatorial surface going right through the equator of the black hole, but it is bent in a higher dimension, which physicists sometimes call the bulk. And it's bent down just like the rubber sheet in my analogy. And the diameter is large compared to the circumference. For a physicist, this is described by the three-dimensional metric, which is a piece of the four-dimensional space-time metric, but it's the metric of space. Now, of course, the thing you all know about black holes is that if I fall into the black hole, carrying a microwave transmitter to send you signals telling you what I'm seeing, there's a surface called the horizon, the surface of the black hole. Once I fall through it, I'm pulled downward to the singularity, and the microwave signals are pulled down, so I cannot get any signals out. Now, then how does that come about? Why is it that gravity is so strong that nothing can get out? Well, I'm going to come there in just a moment. But first I want to say now the warping of space and time, of which the black hole is made, has three pieces. The first is this warping of space, or the three-dimensional metric. The second is a warping of time, so that if you hover just above the horizon, time slows greatly, and right at the horizon, if you're not falling through, time as measured by you slows to a halt. It no longer changes. In the movie Interstellar, Cooper goes down near the surface of the black hole, near the horizon for a few hours, and comes back having only been there a few hours as measured by him, and his daughter has grown from 11 years old to being 28-year-old theoretical physicist. And so you see this very graphically, the slowing of time. Below the horizon, time flows in a direction that you would have thought was a space direction, but it flows toward the singularity. And that is an explanation for why nothing can get out. Nothing can move against the local flow of time. If time is flowing downward, then nothing can swim back against the flow of time. And that's an absolute law of physics. It's just impossible. I'll talk near the end about time travel. You can't do travel this way if you can do it at all. This slowing of time is controlled by another piece of the space-time metric for physicists, the so-called lapse function. And then there's a whirl of space. If a black hole rotates on its axis the same way as the Earth does, then its rotation drags space into a whirling motion, fast near the horizon, more slowly farther away. And that whirling motion is so strong that if you're near the horizon, there's no way to resist it. You get dragged around and around relative to the distant stars, relative to the Earth far away, by this whirling tornado-like motion of space. And this is described by the third piece of the space-time metric in relativity, a so-called shift function. Here is a precise depiction of the warped space-time around a fast-spinning black hole with the horizon down here, and I'm not showing you what's below the horizon. This is the warping of space in the higher dimension. We are very far away where space becomes flat. And you go down to the color shows the slowing of time, where it's yellow, time is flowing at 10% the rate it is back here on Earth. And the angular velocity of the whirl of space is proportional to the length of the white arrows. I'm going to describe in a few minutes how we expect to map that full space-time warpage of the big black hole with gravitational waves. That's something that I will come to. So you might ask, what is it that warps the space and time of the black hole? And the answer is, warping of space and time is always produced by huge amounts of energy or mass. But where is the energy that produces this warping? Because there's no matter present at all. And the answer is the energy is contained in the warping itself. So in technical language, the black hole is held together by its nonlinear self-interaction, or it's a gravitational solitron. If you take this rubber sheet that I talked about and you push down with your fist, you have to do work to bend it. And you have thereby stored energy in the stretched rubber. That similarly here, the warping of space has huge amount of energy stored in that warping, and that energy is the thing that produces the warping. So it's really quite interesting example of nonlinear physics. Now, if I put my wife, Carolee Winstein, at the north pole of the black hole, and I don't care whether she's falling in or just hanging there, her feet will be dragged into whirling motion faster than her head because her feet are closer to the horizon of the black hole. And so as her head looks down and sees her feet are whirling around in a counterclockwise direction. But if her feet look at her head will turn in a counterclockwise direction. So there's actually a counterclockwise twist of space at the north pole of a black hole. It's like taking a wet towel and removing the water from it by turning the wet towel, twisting it. Your left hand sees your right hand twisting counterclockwise. Your right hand sees your left hand twisting counterclockwise. Similarly, at the south pole of the black hole, there's a clockwise twisting of space. We use the phrase vortex that comes from fluid mechanics, from vortices of whirling air or water. To describe this. So there's a counterclockwise vortex at the North Pole and clockwise vortex at the South Pole. I will return to this a little bit later and ask the question, what happens to these vortices when two black holes collide? It's just sort of a preview of some interesting things we've discovered through computer simulations. But let me just continue with black holes by themselves. We now know there are roughly 10 million black holes in our Milky Way galaxy and 10 to the 18 black holes in the entire universe. They have masses that have been measured range from about 3 times the mass of the sun to about 20 billion times the mass of the sun, 2 times 10 to the 10 solar masses. Diameters ranging from 10 kilometers to 100 billion kilometers, so a huge range of sizes of black holes. What would a black hole look like to your eyes if you were there, or to a camera? So if you have a star here, a light ray can travel to the star, from the star to the camera, along the closest thing there is to a straight line in this warped or curved surface that is the space of the black hole. So this, again, as seen from the higher dimension, as seen from the bulk. So the camera will see one image of the star in this direction. But a light ray can also travel around in that path to the camera, and so the camera will see another image of the star in that direction. There will be a shadow region where it can't see any stars in here. And a light ray can travel down around the black hole once and up to the camera, so there may be a third image. And so, in fact, this is from a computer simulation. There are 3 images then, one very near the shadow of the black hole, these 2 farther away, carried by those 3 different light rays. Now, suppose that you have many, many stars. Each star will produce a number of images. And this is a movie that was made by Oliver James, who is the chief scientist at Double Negative visual effects company, who made the images that you see of black holes for the movie Interstellar. He made this using equations that come from Einstein that I put into an appropriate form for him to solve on a computer to make this image. And I want you to watch the patterns of these stars as the camera travels around the black hole gradually. And there is what is called an Einstein ring here of strange, rapidly moving stars. There's another Einstein ring down here. If you look more closely, you will discover there are 2 images of a star created in pairs, and one shoots off to the left and the other shoots off to the right. And then each image annihilates against another image of a star. So we have multiple images of stars down here. And then there are more and more Einstein rings as you get closer to the horizon of the black hole. Really quite interesting phenomena of how a black hole would look as seen against the stars, a field of stars. How does this come about? Now, this is so my talk will have little nuggets for physicists and mathematicians, but most of it will be understandable to everybody. But each Einstein ring can be understood in the following way by a mathematician or physicist. You take the camera, look at the camera's past light cone, which is generated by light rays that come to the camera. And if you follow the past light cone, ultimately adjacent light rays cross, and that forms a caustic. And the caustics then, far away on, you think of a celestial sphere where the stars are located, they make some pattern. There's sort of a rectangular type pattern, the caustics on this celestial sphere. And each Einstein ring is the image of the intersection of the celestial sphere with the caustic of the camera's past light cone. So there's some beautiful mathematics involved here in relativity theory. And when a star on the celestial sphere passes through a caustic, 2 images are created. When it passes through the caustic the second time, 2 images are destroyed. And so there's some beautiful mathematics. It's also associated with what's called catastrophe theory in mathematics. It's all tied up in here. If you want to see the details, the team at Double Negative who made these images and made the images for the movie Interstellar and I wrote a paper about making the image for Interstellar, but also about the things we learned about caustics and gravitational waves, about caustics around black holes in classical and quantum gravity. In the movie Interstellar, you don't see, however, a black hole in that way. It looks like this. This is Interstellar's black hole Gargantua, as seen in the movie, and that image is readily understandable. You have a hot disk of gas around the black hole, and a light ray from the top back face of the disk goes up over the black hole and down to the camera, so the camera thinks the top back face is up there. And that explains this part of the image. And a light ray from the bottom back face is pulled under the black hole by the warping of space and time around the black hole and up to the camera and by gravity. And so the camera thinks the bottom back face is down here, and that explains that piece of the image. And then a light ray from the front of the disk, the camera is just above the equatorial plane, just above the plane of the disk. It comes straight out to the camera and makes this crossbar. So a very simple explanation. Recently, last spring, a collaboration of physicists and astronomers called the Event Horizon Telescope Collaboration made an image of a black hole actually with their telescopes. Their telescopes is actually a combined data from many radio telescopes worldwide looking at 1.3 millimeter wavelength radio waves. So from the South Pole up to near the North Pole, from the Americas over here to Europe. So a worldwide network. 400 scientists and engineers at 100 different institutions. Success last spring, making an image of the black hole in the galaxy M87. This was what the image looked like. And from the details of the image and knowing how far away this black hole was, they could measure the mass of the black hole. It was 6 billion times the mass of the sun, a giant black hole. That doesn't look very much like the image in the movie Interstellar. So what's wrong? What did we get wrong? Because that's really a picture, an astronomical picture on the right-hand side. And this is the black hole in the movie Interstellar. Well, Oliver James, who was responsible for this image, made a little movie to explain. In Interstellar, the camera is just above the plane of the hot disk of gas that's around the black hole. And if you now just move up to the North Pole, you get a new image. And then you blur that image out because the resolution of the radio telescope is not all that good. There it is. With one exception, it's very bright on one side and dimmer on the left-hand side. We didn't have that in the movie Interstellar. The reason was that Christopher Nolan, who was the director of the movie Interstellar, said, I want this to look like it would look like to your eyes. And a very bright source of light, you can't distinguish brighter or dimmer. It's just very bright all the way around. And so he made it without this brightening on one side. So that was the only thing we had wrong. We knew we had it wrong, and we knew why. Okay, let me turn to gravitational waves, the second example of an object on the warped side of the universe. Albert Einstein predicted the existence of gravitational waves in 1916. He said that if a gravitational wave propagates into the screen, then it will stretch space horizontally while squeezing it vertically. And then a moment later, stretch it vertically while squeezing it horizontally. There will be no stretching and squeezing along the direction of the wave propagates, just transverse. That's similar to electromagnetic waves, where an electric field oscillates, or electric force oscillates transversely in an electromagnetic wave, and a magnetic field transversely, purely transverse waves. What does this mean to say space stretches and squeezes? Another way to say it in technical terms is if you have an inertial reference frame over here and an inertial reference frame over there, a particle at rest in this inertial reference frame will remain at rest. And one at rest in that inertial reference frame will remain at rest. But the inertial frames are moved back and forth relative to each other in this stretching and squeezing of space. So that's a more technical description. And here are those particles, each at rest in its own inertial frame, but the pattern is stretching and squeezing. There are only two types of waves, according to the laws of physics as we know them, that can be created in the distant universe and travel across the universe, bringing us information about what's far away. There also are particles, cosmic rays, and neutrinos, but I'm just talking about waves. Electromagnetic waves, light, radio waves, X-rays, gamma rays, they're all made of oscillating electric and magnetic forces. It was Galileo 400 years ago who created modern electromagnetic astronomy by building an optical telescope, pointing it at the sky and discovering the 4 largest moons of Jupiter. And the other is gravitational waves. So the goal of the collaboration that I have been involved in, the LIGO collaboration and the Virgo collaboration, has been to do what Galileo did for gravitational waves, to create a gravitational wave telescope or detector and to build one and observe something and thereby do the first step in creating gravitational astronomy. So it's the modern analog of Galileo. Now, gravitational waves are a stretching and squeezing of space, so they're a warping of space. They're made then from the same thing as black holes, a warped space, warped time. We think of space and time as unified in relativity theory, so it's a warped space-time. Is what a gravitational wave is, made of the same thing as black holes. And that means that gravitational waves are the ideal tool for exploring black holes and other objects that are on the warped side of the universe. Something that's made from pure warped space-time cannot emit electromagnetic waves, only gravitational waves. So gravitational waves are the tool for exploring the warped side of the universe. 1972, Ray Weiss at MIT proposed the kind of gravitational wave detector that was ultimately successful. There had been earlier work with what are called bar detectors that was pioneered by Joseph Weber, and bar detectors were built here in Italy by Eugenio Coccia and his collaborators, and in various other countries around the world. But the ones that ultimately had the success were the kind that Ray Weiss invented, but we built very much on the developments also with bar detectors. Ray said, let's do the following. Let's hang 4 mirrors from overhead supports along one arm that is, say, going east-west, another north-south, so they're perpendicular arms. When a gravitational wave comes by, it will push these mirrors apart and push those together if the wave is oscillating at frequencies high compared to 1 hertz. That 1 hertz is the normal swinging frequency of a pendulum, and these mirrors are pendula. And it's, if you try to push them at lower frequencies than that, the restoring force sort of doesn't let them respond. But at higher frequencies, above 1 hertz, they respond as though they were not on the ends of pendula. And so he said, look for gravitational waves with frequencies high compared to 1 hertz, and then the waves will push these mirrors apart while those are being pushed together, then push these apart while those are being pushed together. And he suggested that we use a technique called laser interferometry to monitor those motions. I'm not going to go into details at all. This is not a lecture about the technical details of gravitational wave detection, but just to say you're using laser beams to make these to measure that changing difference in the separation between the mirrors. He called this a gravitational wave interferometer. I'm going to skip over all the history between then and now, then and recently. Simply say that after 43 years of intense work by a team that grew to more than 1,000 scientists and engineers led by Barish, we finally had gravitational wave detectors that had success. And therein lies a very interesting and complicated story, both technologically, politically, and human, that I'm completely skipping over. What happened was 1.3 billion years ago, when here on Earth, multicelled life was just forming and spreading around the world. But far, far away, in a galaxy far, far away, as our friend Carl Sagan used to say, 2 black holes circled around and around each other, and this is from a computer simulation corresponding to the first gravitational wave signal that we saw. So computer simulation was key to understanding what we were seeing when the gravitational waves came in. So the 2 black holes circled around and around each other. You can just see their shadows. This is light, and there's a Einstein ring. As they circled around, they gradually lost energy to the gravitational waves. They spiraled together, and they finally came crashing together in a huge cataclysmic collision. They produced a very strong burst of gravitational waves that traveled out of the galaxy in which the black holes lived into intergalactic space. For 1.3 billion years, they traveled across intergalactic space. They reached the outer edges of our Milky Way galaxy 50,000 years ago, when our ancestors were sharing the Earth with the Neanderthals. They traveled into the Milky Way galaxy, across the Milky Way galaxy. They arrived at Earth on the 14th of September, 2015. The LIGO team it's an international collaboration of, at that time, about 80 institutions around the world, and I think at that time about 14 countries. The LIGO team had built a pair of advanced gravitational wave detectors. They were being prepared to start their first search for gravitational waves. The first search was scheduled for 3 days later. The detectors were being tuned. They're very complicated detectors. They were being brought into the final configuration to begin the search when the signal came in. And David Wrightsey, who was the director of LIGO at the time, he declared when the signal came in that the first search had started 3 days early because we got a signal. The configuration of the detectors was frozen, and the first search then continued for several months thereafter. This gravitational wave burst then arrived at the southern tip of the Antarctic Peninsula, and it traveled upward through the Earth, emerging through the Earth first at the LIGO gravitational wave detector in Livingston, Louisiana. Inside of this long cover, there's a pipe, and inside of the pipe is the laser beam going back and forth between the mirrors that are hanging 4 kilometers away from the corner mirrors. And down this pipe, a laser beam. And the gravitational wave stretched and squeezed the space between the mirrors at the ends of these arms. And the signal was measured by the technique that Ray Weiss had suggested, and that was improved upon, and huge progress made in developing the technology by this large team. 7 milliseconds after the signal arrived at Hanford, Washington, in Livingston, Louisiana, the signal came up through the Earth at Hanford, Washington. Livingston is roughly to the south of Hanford. So that's how we knew the signal was coming from the south, because it arrived at Hanford first. That's how we know that it entered the Earth somewhere near the Antarctic Peninsula. At that time, then, there was a collaboration between LIGO, the team that built those particular detectors, and the Virgo collaboration that was created by a group of physicists here in Italy and in France. And the combined LIGO-Virgo team analyzed the data, and it took 5 months of analysis by the LIGO-Virgo scientists to be absolutely sure that this was really a gravitational wave. And what we found was that it was truly real. These instruments are so complex. There are 100,000 data channels comes out of each instrument, because there are so many things can go wrong. So monitoring the instrument, the interior of these instruments, and monitoring the environment around the instruments, this huge number of data channels, crucial ones of which were examined by the young members of the team to be absolutely sure this really was a gravitational wave, was not due to anything else. And when we were sure the actual shape of the wave, the stretching and squeezing, stretching up and squeezing down as time passes, after the data were cleaned up, was the gray trace here. And the red trace is from a computer simulation by something called the SXS collaboration. It was Caltech and Cornell at that time. The SXS collaboration got extremely good agreement. If this really was a collision of 2 black holes, the 2 black holes then were inferred from the simulation that gave the waveform that matched the observation to be 29 solar masses and 36 solar masses, for a total of 65 solar masses. The final black hole was 62 solar masses. So there was 3 solar masses missing. It was as though you had annihilated 3 suns. and turned all of their mass into gravitational waves and sent them out through the universe. This happened so fast in about 1/10 of a second that the total power output was 50 times larger than the total power that comes off of all of the stars in the universe put together, but only for 1/10 of a second. It's still 50 universe luminosities, 50 times the power of all the stars in the universe put together, coming off from these colliding black holes. And the distance was also inferred from comparing with the simulations at 1.3 billion light years. We announced the result on February 11, 2016, and it made front page headlines in all the major newspapers around the world. We have now have the Virgo gravitational wave detector has joined with the LIGO gravitational wave detectors and have been working together, making observations since August of 2017. They were then shut down for upgrades, for improvements, and have been carrying out the third gravitational wave search together, began on April 1st with improved interferometers. In that time then, the searches up until now, the LIGO-Virgo collaboration with the 3 detectors now, one near Pisa, Italy, the Virgo detector, and the 2 LIGO detectors in North America, they've seen more than 30 gravitational wave signals now. You can get for your smartphone an app called GW Events. And if you then put that on your smartphone, it will go whoop, making a chirp, because that's what a gravitational wave signal from colliding black holes makes if you put it on a loudspeaker. It will go whoop within 1 hour of when any gravitational wave signal arrives. The LIGO Virgo team has this all automated. And so I'm showing here, for example, during the last 2 months of observation, for the current month of October, the detectors are shut down to be improved a little bit just this month. So from late July, the July 27th, 2019, you read this off from the name of the gravitational wave signal, up to September 30th, 2019. These are things that you'll find on your smartphone if you have the app. These are the details of all those gravitational wave signals over a period of about 2 months. 10 events in 2 months, roughly 1 a week. 5 of them were collisions of black holes. 1 was a collision of 2 neutron stars. The first neutron star collision that was ever seen was spectacular. Electromagnetic waves were seen from it, all forms of electromagnetic waves as well as gravitational waves. This neutron star collision, the electromagnetic signals have not been seen. It was farther away, the electromagnetic signals were weaker, and only 2 of the 3 detectors saw it, and so we did not have a good, because one of them was not working properly at the time, so we don't have a really good position on the sky. There have been 2 examples just very recently, quite recently, of a neutron star, a star that is made of pure nuclear matter that has a diameter of about 30 kilometers and weighs maybe 1.5 times what the sun weighs. 2 neutron stars being swallowed by black holes. No electromagnetic signals seen from them. And just very recently, 2 things that are called mass gap signals. We've never seen any object between very compact object between 3 solar masses and 5 solar masses. We think they are probably black holes in that range, but nobody had ever seen any. Conceivably, you have neutron stars in that range, but probably not. And it was always a big mystery. Are there any such objects, cold, dead objects, in the universe between 3 and 5 solar masses? Well, we saw 2 of them. One with 100% confidence on September 24th, another with 95% confidence on September 30th. Just amazing. They came in one right after the other. This gives you some sense of what's happening now. By the late 2030s, 20 years from now, there will be, we expect, we hope, successors to LIGO and Virgo, larger detectors, more sophisticated on the ground, called Einstein Telescope for the one in Europe and Cosmic Explorer for the one in the North America. And they will likely see waves 20 times weaker than any waves that are seen today. They will see every black hole collision in the universe with masses less than 100 solar masses. They will see a variety of other warped side of the universe phenomena. And also by the 2030s, we expect to be seeing gravitational waves in 4 frequency bands. I remind you, for electromagnetic waves, the only difference between radio waves, optical light, X-rays, and gamma rays is the frequency of the waves. And so what we expect is that by the 2030s, we will have the gravitational analog of radio astronomy, optical astronomy, X-ray astronomy, gamma ray astronomy, with 4 different kinds of detectors. The LIGO, Virgo type of gravitational wave detectors, looking at gravitational waves with periods of milliseconds. LISA, a European Space Agency mission involving 3 spacecraft that track each other with laser beams, periods of minutes to hours. The difference between this and that is about the same as the difference between radio waves and optic and light. So this is the analog of radio astronomy. That's the analog of optical astronomy. And with LISA, we expect to see black hole collisions with masses between 1,000 solar masses and 10 million solar masses. Expect to map black holes with exquisite precision. I'll talk just a tiny bit about that. And observe the birth of the electromagnetic force at the beginning of the universe. With a different technique called pulsar timing arrays, we expect to be seeing gravitational waves with periods of years to decades. And with these, we'll see gigantic black holes, up to 10 billion solar masses. And then by a technique very different that I'm not going to go into details, but it's called CMB polarization, we're going to see gravitational waves from the birth of the universe with periods of hundreds of millions of years. That's a little long compared to the life of a graduate student. So you don't wait for the waves to oscillate. You look for a pattern on the sky of what's called polarization of microwaves. And then in the middle of this century, a successor to the LISA mission that will see these waves from the birth of the universe with periods of seconds compared to hundreds of millions of years. There's a great future. I'm going to talk for just a few minutes about some of the science that we expect to see with LISA and these other instruments. So this is an old version of LISA. I think, is LISA back now officially to 5 million kilometers? Arm length? No, I think. Anyway, LISA, I remind you, is a European Space Agency mission with 3 spacecraft that track each other with laser beams. LISA will see then giant black holes with masses of millions of suns. But one of the most interesting things from my point of view is that if you have a small black hole orbiting around a big black hole, the small black hole will create ripples in the shape of space as it goes around the big black hole. Those ripples travel out and become gravitational waves. And those waves carry a full map of all features of the space-time geometry, of the warping of space and time of the big black hole that's being explored, being seen by the small black hole as the small black hole goes around. You might ask, how can it possibly get the entire map if it's just going around and around like that in the equatorial plane? Well, the answer is it doesn't stay in the equatorial plane. The orbit is very complicated of the small black hole. To see what the orbit looks like, I'm going to remove the warping of space and just show you the orbit as though space were flat. So here is the big black hole, the small black hole going around it, and the orbit is very complicated because the orbit is influenced by gravity, by the warping of space, the warping of time, the whirling of space, and that just makes the orbit so complicated that the small black hole basically explores the entire region around the big black hole as it goes around, and sending off a very complex gravitational wave signal that carries the map. So we expect with LISA to map with exquisite precision the geometry, the details of the warping of space-time of big black holes in the same way as we humans have mapped the surface of Mars or the surface of Venus or surface of planets. What if the central body isn't a black hole? For example, suppose it was a naked singularity. I won't tell you what a naked singularity is. I've told you there is something called a singularity, where the laws of physics as we know them break down inside black holes. There's a big question whether these singularities can exist outside of black holes. Well, here, if you had a naked singularity of a particular variety called a Manko-Novikov singularity, the orbit of one of these, of a little black hole going around that singularity is actually chaotic. It's quite interesting. The orbits down here near this singularity are mathematically chaotic, whereas the orbits farther away are not chaotic. And you have a rather unique and a bit surprising phenomenon in the same space-time, in the same warped space-time. You have regions with chaotic orbits, mathematically chaotic, and regions that have non-chaotic orbits. So that's a remark for mathematicians who know about the theory of chaos. And this, of course, gives you a wildly different map from what you get from an object going around a black hole. So we will attempt to search for naked singularities. LISA will, the European Space Agency's mission, by mapping, by using gravitational waves from orbiting objects to map the space-time geometry of the central body. One other thing that we're doing in this field is studying the dynamics of space-time geometry, the dynamics of warped space-time when black holes collide. So, and we explore this by computer simulations combined with observations. We see a gravitational wave burst from colliding black holes. We determine the properties of the black holes by comparing with computer simulations. We adjust the masses of the black holes and how the black holes spin until we get a very good match between the shapes of the waveforms from the simulations and what is observed. Then we go back to the simulations and see what was warped space-time doing. So here is the warped space-time of that we infer from the computer simulation that matched the first observed gravitational wave burst from September 14 of 2015. Each black hole then looks like a funnel. It goes down. The color coding is the slowing of time. The little arrows are the dragging of space into motion, or in technical terms, the three-metric, the piece of the three-metric in the orbital plane, the lapse function and the shift function. But just a remark for the mathematicians, although you can take a two-dimensional surface, like the orbital plane of these two black holes, and always embed it locally in a three-dimensional flat space, which is what's being done here, you cannot do it globally. If you go in and you try to do it, you go around a black hole, you come back and things will not match up properly. So a cheat has had to be done here because this cannot be done globally. And so there's a kludge, but I'm not going to tell you the details of the kludge. If you want to ask me privately later, you can. But this gives you a sense of what happens in that collision. The black holes go around each other. I'm slowing the movie now because the black holes are about to collide. I'll bring it to a halt as the black holes collide. This creates a gigantic splash in the shape of space, an oscillation of the color-coded flow of time, like what you would get in a huge storm at sea on the ocean. And the gravitational waves go flowing out. So that was a picture then of the equatorial part of the space-time geometry in the first black hole collision that was seen. But this movie actually captures only a small portion of the space-time storm that is created by the black hole collision. That storm, the dynamics of warped space-time, is what John Wheeler, my PhD advisor, called geometrodynamics, the dynamics of geometry of space-time. And he urged his students, his colleagues, his postdocs, to solve Einstein's equations to predict how to predict the details of geometric dynamics. And it was obvious to him already, and this is before I was his student in the late 1950s, it was obvious to him and his students that this could not be done by pencil and paper. And so the first efforts at computer simulations started in his research group at Princeton, triggered by this desire to study geometric dynamics. So I'm going to tell you a little bit about what we have learned about geometric dynamics beyond what you saw in that movie. I told you about vortices, counterclockwise vortices and clockwise vortices sticking out of a black hole. So let's suppose we have, for the simplest example possible that's interesting, two black holes. They are falling toward each other, moving toward each other. They're going to collide head on. And this one has a counterclockwise vortex sticking out of the North Pole, clockwise sticking out of the South Pole. I don't show the vortices. I just show the colors to indicate what kind of a vortex, clockwise or counterclockwise, is sticking out of the black hole. And we will watch what happens if the black hole collides. So here the counterclockwise or blue vortex is up. The red or clockwise one is down. Here the red clockwise vortex is up. The counterclockwise is down. Remember, this is just twisting of space in the two-handedness. So the black holes fall toward each other. This is, again, a simulation by this SXS collaboration. And it's quite amazing. You look in the upper right, this is red, then it was blue. It oscillated from red to blue to red to blue. Let me just run the movie one more time. So these vortices exchange polarity. It was blue, now it's red, now it's blue. The black hole is oscillating, the shape of the black hole is oscillating, and the vortices fight with each other and trade direction of twist. This was discovered in computer simulations, actually by a group of students who were working with me and my successor at Caltech, Yan-Bei Chen, who now leads the research group that I used to lead. What's going on? Well, first, at the moment when you see red on one side and blue on the other, these vortices have reconnected. And I'm showing you now the paths of the vortices. These are actually vortex lines, by analogy with vortex lines in fluid mechanics for people who know about vortex lines. But these are the things that guide the twisting of space. These are the axes around which differential precession of space is occurring, or differential twisting is occurring. And they've reconnected, so there's a vortex coming out off of this red spot, and it goes back into a red spot on the back side, comes out of this blue spot, goes back into a blue spot on the back side. However, and then for the physicists and mathematicians, these vortex lines are actually the integral curves of what's sometimes called the magnetic part of the vacuum Riemann curvature tensor. So you take the Riemann curvature tensor, then you have the analog of a magnetic field and electric field. This is the so-called magnetic part of the Riemann curvature tensor. And these are the integral curves of the magnetic part of the Riemann tensor emerging from the black hole. So this is all tied to some elegant mathematics. Now, as these black hole oscillates, every time this goes green, those vortices are being ejected from the black hole. And then when it regains colors, they're being recreated on the black hole. As the vortices go off the black hole, they kick back at the black hole and create mirror images of themselves, it turns out. So what happens is they pop off the black hole, the clockwise and counterclockwise vortices wrap around each other and form a torus like a smoke ring. And these tori then travel outward, one after another, into space. These are intertwined clockwise and counterclockwise vortices. We never expected anything like this. We saw it in the computer simulations. We now understand it analytically in the mathematics, but only after we had seen it in the computer simulations. If you have a magnetic field, and these are analogs of magnetic fields, and it moves, it generates an electric field. In the same way as these vortices of twisting space travel outward, they generate what are called tendices of stretching and squeezing space. And these have tendex lines. The tendex lines are integral curves of the electric part of the vacuum Riemann tensor, again for physicists and mathematicians. And the tendex lines, stretching tendex lines reach around the torus in this way, and squeezing tendex lines around that way. But on the next torus, the stretch and squeeze directions switch. And so what you really have, and if you want to learn about vortices and tendices and the mathematics underlying all this, the only textbook treatment is in a very recent textbook by Roger Blandford and myself called Modern Classical Physics. So if you go in there to the relativity section, you can read about this, again, for the physicists and mathematicians. I'll very quickly then tell you about observing the birth of the universe and the birth of fundamental forces. Fundamental forces at age 10 to the minus 12 seconds, a trillionth of a second, there was something called the electroweak phase transition. Before this, there was no such thing as electromagnetic force. You had something called the electroweak force that existed throughout the universe, because the universe was very hot at that time. As the universe cooled, this electroweak force came apart, creating the electromagnetic force that was familiar to us, making Maxwell's equations suddenly relevant to the universe. And the weak nuclear force came apart as the other piece. So there was this phase transition. Phase transition may have occurred in what is called a first-order form. If so, then it occurred inside bubbles, like bubbles of water droplets forming out of water vapor. But these bubbles, by contrast with water droplets, expanded at near the speed of light, collided, and produced a burst of gravitational waves in the collision. Those waves have been shifted to longer wavelength today. They're in LISA's frequency band. So LISA will search for gravitational waves from the birth of the electromagnetic force. Then there are primordial gravitational waves with periods of hundreds of millions of years that are produced in the Big Bang as tiny, tiny waves. They get strongly amplified, according to theory, by what's called inflation in the earliest moments of the universe. And these gravitational waves then, I won't say how, they put this polarization pattern on the microwaves that are created when the universe is about 400,000 years old. And today we search for that polarization as the holy grail of studies of the radiation coming off the birth of the universe. The spectrum of these waves will be a mixture, technically a convolution, of whatever came off the Big Bang and the effects of inflation. And so by studying the spectrum of these waves, we can get some handle on what happened in the Big Bang and how the inflation influenced it. By around 2050, a successor then, as I said to you earlier, to LISA, called the Big Bang Observer, which is a constellation of several LISA-type sets of spacecraft that track each other with laser beams. The constellation going all the way around the Earth's orbit will be able, we expect, that is the plan, to see these same primordial gravitational waves with periods of seconds instead of periods of hundreds of millions of years. To see primordial gravitational waves, each of them carrying information that's a convolution of the birth of the universe and inflation, in two such widely separated frequency bands will really be remarkable. There's a prediction of what will be seen based on conventional physics, and I look forward to the day when that prediction turns out to be false, and it forces the theorists to go back to their drawing boards and rethink their understanding of the laws of quantum gravity. I'm going to, in the last several minutes, wind up by talking very briefly about wormholes and time travel. I didn't advertise this in the title, but these are topics about which people often ask questions. They're things that we asked questions about when I was a student, and we have learned something. So a wormhole is can be understood in the following way. And this is a variant of it that was used in the movie Interstellar. Imagine our universe, and we have a two-dimensional surface in our universe, bent in the higher dimensions, bent in the bulk around, so that if you travel from the solar system near Saturn to a distant galaxy, it might be 10 billion light years, but it might be only a few kilometers across the bulk if you could travel across the bulk to get from our solar system to this distant galaxy. There could conceivably be a wormhole, and now the surface of this wormhole is part of our universe. You're only seeing two dimensions, so you imagine your two-dimensional self traveling down through that wormhole. Or you imagine then a camera here looking at nebulae in the distant galaxy with light that comes through the wormhole. So the paintings of the distant galaxy for the movie Interstellar were made by a team led by Eugenie von Tunzelmann at the Double Negative Visual Effects House in London. I then gave to Oliver James the equations to propagate light beams from that distant galaxy to the camera, and he then made a movie of what it looks like to travel through the wormhole. This movie is a little different from the movie you see in Interstellar. This is the real thing. This is a precise depiction for the particular wormhole that was used in Interstellar. This wormhole has a size of a few kilometers, but it's very close to us. Saturn is much farther away, so they look about the same size. But there are two images of Saturn from light rays that go around the wormhole on this side and around the wormhole on that side. And as we fall into the wormhole, we'll see these images distort. So we're starting into the wormhole in this computer simulation. The images of Saturn distort, get pushed off to the side. We're now entering the wormhole. We're traveling through the wormhole, and we're now out the other side. Now, when Christopher Nolan first saw this, he telephoned me. He said, "We have a problem with our movie." And I said, "What's the problem?" He said, "The wormhole trip is not exciting enough." And so I went over, and he said, "I've had them do a number of different shapes of wormholes, and it's never very exciting. And what do we do?" And I said, "This is the one place in this movie where you use your artistic license." We had agreed that we would make this movie follow real science unless that got in the way of making a great movie. If it got in the way, then we would give up and use artistic license. This is the one place in that movie where artistic license is used. And so it's a more interesting trip, but it looks something like that. Anyway, that's the trip through a wormhole. The problem is, as John Wheeler, my thesis advisor, and Martin Kruskal discovered in 1960, that wormholes collapse if you don't do something to prevent them from collapsing. So here I have a photon, a particle of light that's headed down and traveling at the speed of light through this wormhole. But as it starts to travel, the wormhole pinches off, and the photon gets caught in the pinch-off. The pinch-off creates two naked singularities, and the photon doesn't get through. And the only way to avoid this, we came to realize fairly easily, is you have to have something inside the wormhole that causes the walls of the wormhole to repel each other gravitationally. And that has to be something that has negative mass or negative energy that repels gravitationally. And at first sight, you might say, well, that's impossible. But in fact, there are substances, materials, call them fields, in physics called the Casimir vacuum, the squeeze vacuum, that have just this property, negative energy, locally or for a fleeting few moments. I won't go into the details, but The squeezed vacuum is crucial for LIGO technologically. Casimir vacuum is very interesting, has been studied experimentally. We know you can make negative energy. The laws of physics say that should anti-gravitate, so that's what you need to hold a wormhole open. So what's the story with wormholes? Can they occur naturally in the universe? Our answer is almost certainly no, those of us who've spent several decades trying to study it. Can they be made by an advanced civilization? Possibly. As Wheeler was the first to speculate, it may be that on very small scales called the Planck scale, that there is a foam of wormholes that fluctuate in and out of existence, so-called virtual wormholes. You could imagine an ultra-advanced civilization grabbing one of these and enlarging it to a big size. It's just pure imagination at this stage, but it's not out of the question. Once you have one, can it be held open? There, a lot of work has been done. The bottom line is probably not. It requires too large amounts of this exotic matter, and it appears the laws of physics may not allow you to have enough. But when speculating beyond the frontiers of firm knowledge, I've been proved wrong many times, sometimes spectacularly, so don't take my pronouncement that wormholes probably can't exist too seriously. And finally, just a few words about wormhole-based time travel, and I'll quit. If I have a wormhole, I keep one mouth in my home in Pasadena, California, and my wife, Carol Lee, takes the other mouth on a very high-speed trip out into the universe and then back. There's something called the twins paradox, which is a firm prediction of special relativity, that has been verified observationally with fundamental particles. That when she goes out and comes back at high speed, I may have aged by 10 years, and she might have only aged by a few hours. And so that's what it will look like when we look at each other. When she's back here, and she looks at me, and I look at her, I'm old, and she's still young. When she lands back on Earth and comes to our house, bringing her wormhole mouth with her. But if so looking through space, Carol Lee sees me old. But if we hold hands through the wormhole during the entire trip, and we look at each other's watches, the watches will tick at the same rate, quite obviously, down inside. So as seen through the wormhole, there's no differential aging. As seen through the wormhole, she sees me as still young. So that means that if I just as an old man is seen by her when we're back together, I go down and I enter that wormhole mouth, I'll meet my younger self. I have a time machine. In 1991, a postdoc of mine and I discovered, however, that at the moment that a time machine is first created in this way or in any other way, it probably self-destructs. I'll just say a few words about that. The key thing is that vacuum fluctuations, the same things as make possible this Casimir vacuum, make possible negative energy. Vacuum fluctuations will travel through the wormhole and back at the moment when the wormhole first becomes a time machine. They will travel through the wormhole, then back through the external space, arriving back at the same moment as they started, and now have twice as much of this strange fluctuations. And it starts to have a lot of energy. Goes around a second time, you have even more, a third time, and you build up a huge, intense beam of these fluctuations with enormous amounts of energy that very possibly destroy the wormhole at the moment that it first becomes a time machine. Here's an article that treats this from a very different way for people who want technical details. It is a highly rigorous demonstration, similarly, that something very weird is going on explosively at the moment that you first get a time machine. Is the explosion strong enough to destroy the wormhole? Only the laws of quantum gravity know. We don't know whether or not they do. And that was a conclusion of lots of calculations by Stephen Hawking and his students, and a little bit of work in my research group. Stephen Hawking, however, was quite convinced that the time machines will always be destroyed when they're first created. And so he proposed the chronology protection conjecture, that time machines, when first turned on, will always self-destruct, thereby keeping the universe safe for historians who might have trouble creating histories if you do have backward time travel. So that's where we stand. That's what we've learned in the 50 years since I was a student and a young professor. Today, 60 years after our early speculations, we've observed black holes, we've observed gravitational waves, we know a lot about the Big Bang. These are all real things. We doubt wormholes exist. We doubt backward time travel is possible. And in the future, gravitational waves, in fact, are likely to reveal great details of things we have never yet dreamed about concerning the warped side of the universe. Thank you.
So we, of course, thank a lot Kip Thorne for this wonderful conference. And we have some, I think, some suggestions for further reading and further learning about all what he said. There are questions or comments? Any kind of questions and any kind of comment are welcome.
It's obvious that everybody understood absolutely everything I said, because there's no way there can't be any questions unless that's the case.
Elisabetta, come here.
I just wanted to ask you maybe to discuss something you did not talk about explicitly. You said you were not talking about the singularity and what in particular, when it's a naked singularity, if you can tell us something about that.
So a singularity is a place where the laws of physics as we know them fail, and presumably these new laws of quantum gravity take over. These are the same laws as control the birth of the universe, and we want to explore them by making observations of the birth of the universe. They're the same laws as we think control whether or not time machines destroy themselves. And so these singularities are phenomena that we do know examples of. The Big Bang singularity in which the universe was born, that's an example of a singularity. And then we now know, as a result of a lot of work over several decades of time, that there are three different singularities inside a black hole. One is a very chaotic and destructive singularity that if you fall in there, you get stretched and squeezed in a chaotic manner, and ultimately, after you're dead, the atoms the body's made of get stretched and squeezed chaotically, and ultimately the laws of quantum gravity take over. There are two other singularities, though, that are not widely known. It's not so widely known. If you fall into a black, and these are used in the movie Interstellar. So if you want to see a discussion of this, my book, The Science of Interstellar, has a chapter on it. If you fall into a black hole, time is so compressed inside there that everything that will fall into the black hole in the future billions of years comes down after you in a fraction of a second. It forms a shock wave that is a rather vicious shock wave. And everything that fell in the past, a little bit has gotten scattered back up, and it forms a shock wave. And so you're sandwiched between two shock waves with a chaotic singularity below we think below the upgoing shock wave. These shock waves are what in the movie Interstellar are called gentle singularities, in the sense that you get stretched and squeezed, but not chaotically, just one stretch and squeeze. It happens so fast, however, that when you hit the singularity, you're still maybe you've only been stretched a few percent, perhaps. And so there's some small possibility you might survive, and Cooper survives in the movie. Naked singularities are things that we have mathematical examples of, but we strongly suspect that they cannot form in the real universe. But we have an example that if you can have wormholes and they pinch off, they would create naked singularities. So that's one way they might form, but we think you probably can't have these wormholes. So there's a lot of unknown stuff about singularities here, and that I've told you basically everything we know in 3 minutes.
So after a question from a physicist, a question from a mathematician.
It will be not a mathematical question.
Good, because I'm not very deep in the math.
Just something that simulated is more speculations. Just going in speculation because what you said actually is that a wormhole very likely will not exist. That was your claim. So imagine that this morning we were talking about a visionary physicist, scientist,
yes.
You remember? And imagine a crazy visionary scientist who would like to find something to observe, including the fact that you have these quantum effects inside, so you should have observable stuff even there.
Yes.
So where this crazy visionary scientist could start, in your opinion, to try to see something?
Yeah, so of a naked singularity, or are you talking specifically about naked singularities, or I'm sorry, about wormholes? So the best person to ask is Igor Novikov, an esteemed colleague of mine in Moscow, who has been looking at these questions. And I'll just give you one example. So if you have a wormhole and stuff falls in from one side, being pulled gravitationally, it will go shooting out the other side. And so you can imagine having a wormhole with stuff flying out of it, basically a source of matter or radiation that's flying out. And so he's built various models of this sort. But that assumes a traversable wormhole, which is what he has been exploring.
Carmelo, ti lancio il microfono.
I would really like to get questions from students, but...
So thanks a lot, first of all. I mean, it was really a pleasure to listen to your talk. I have a question about the future of science. So do you think that also thanks to you, it will be more common in the future to have to use money from Hollywood movies to convince people to fund fundamental research with a tiny fraction of the cost of an Hollywood production, to use this money to grant fundamental research?
So I assure you that we at Caltech have been asking ourselves that question. We have not yet figured out a good way to tap Hollywood for funding. It's a lot easier to get money for fundamental research from people in Silicon Valley than Hollywood, but we're working on it. There are few people in Hollywood who are really close to science. There are some, but very few, and they have tended to choose to, if they're giving money away, they have tended to choose to put it into things that are more likely to influence humanity today than to foster science that will have a big impact in the future. But we hope to make that change.
More questions?
There is a long-lasting debate, and I would like to hear your stance on that. Do gravitational waves transfer energy?
So this is a debate that I think was actually resolved in a very convincing and solid way by Richard Isaacson, who at the time was a student of Charles Misner at the University of Maryland, and who became, it's often said that LIGO was founded by Kip Thorne, Rainer Weiss, and Ron Drever. But in fact, it was 4 people, Isaacson and us. Isaacson was our program director at NSF. And having done spectacular work on precisely this question, he went to NSF and became the driving force in Washington who made LIGO happen. Absolutely crucial role. And there is now a prize from the American Physical Society in Isaacson's name for contributions to gravitational physics because of him. So what Isaacson did was and I'm going to get a little technical for the mathematicians or physicists, he did a 2-length scale expansion of Einstein's equations, treating gravitational waves as very short wavelength perturbations of the shape of space and time, and that are propagating through a gently curved, gently warped space and time of the rest of the universe. And by this simple technique, a technique that is also used in other places in mathematics and physics, for example, in the theory of boundary layers and fluid mechanics, he was able to show rigorously gravitational waves carry energy. He quantified that energy. He was able to show that the energy in gravitational waves warps space, large-scale space and time in just the manner that you might expect it to if it were any other form of energy. So it was a real tour de force analysis. And those who have doubted it ever since are looking for a proof or a discussion of this that is exact, mathematically exact. And I think you will never find it. The gravitational waves carry energy in an approximate manner, but still that is highly accurate, only in this limit where the waves have short wavelengths compared to the scale of warping of the rest of the universe through which they're traveling. Okay, excuse me for the rest of the audience, but I think this is an important point that is not much understood outside the experts in our field.
So just a curiosity. I never seen an animation or even a simulation considering the possibility of 2 objects not orbiting one around the other, but just colliding in a close encounter system, let's say. So one of the other in a hyperbolic orbit around. This should be even more frequent, just statistically. So why we do not see it discussed? Because it is too much complicated or small power?
So there are those kinds of simulations for black holes and stars, because there's interesting physics where the black hole tears the star apart as it goes near the black hole. And so I can show you simulations. If I took a minute, I could find one on my computer, where you see the star go near the black hole. It's stretched, and then it leaves behind a long tail, which wraps around the black hole to form a hot accretion disk. And the stuff that goes off forward, it keeps going. For black holes, for 2 black holes, you can do approximate treatments that doesn't require computer simulations if one black hole is small compared to the other, or if the encounter is not too close. But it's true. I don't think there have been any, I don't know of any simulations where they have comparable sizes and they're almost colliding but not quite. On the other hand, I think these will be much more rare than the things that we do see, because black holes are that collide. Black holes that are not already in orbit around each other, the distances between black holes in the universe are so great that they're not going to easily find each other, except near the centers of galaxies or dense star clusters. Then this will happen, but I think we expect that this will be somewhat less common than the things that we are simulating and we are seeing. Nevertheless, we may well see that kind of thing in the future, maybe not too distant future, and simulations are needed. But the focus has been on these things that we were fairly confident would be more frequent, the black holes going around each other. So this is a interesting challenge for the future of simulations and for searches. Searches for these signals will be harder than for the case of 2 black holes going around each other and merging, because it will be a very brief gravitational wave burst, and it won't have a long and well-defined form like the things that we've seen before. So it's easier to find the kinds of things we've seen up until now than it will be to find this. But I think it's likely we will see this, and that's something that now is probably the time that these simulations should be done and searches started in the near future.
Well, Kip, this morning you visited the Gran Sasso Underground Laboratory.
Yes.
So first I would like to have your impression about this visit. And then, as you've seen, there are various experiments trying to detect directly dark matter in the form of particle, weak interacting massive particle. So we have, in the same time, we are detecting a lot of black holes. Are they, or can they from stellar mass collapse, or can they be in part primordial black hole, which is a possible way to explain dark matter without a new kind of particle. In this case, the effort of our friends will be unuseful, and I hope that that is not the case. May I have a comment about that?
Okay, well, let me begin with your second question. I'm not a great expert on this, but I am aware of work that has been done. And there is a range of masses of black holes that could account for the dark matter. And as Mark Kamienkowski and colleagues have shown, there's a relatively narrow range compared to what you might have imagined you would have for black holes. But it is quite possible. And so searches are underway to try to pin that down. But I'm not familiar with details. But I'm just aware that is a possibility. I'm skeptical of that explanation. I think a much more natural explanation is the explanation for which the work at the Gran Sasso laboratory is going on, that this dark matter is fundamental particles and not primordial black holes. But before I talk about that, let me just say, primordial black holes were first speculated about by Stephen Hawking before he did his most famous work on black holes. And they still are a real possibility. And they are worth searching for. But I just personally am skeptical that that's what's explaining the dark matter that we now see. The best expert, if anybody's curious, go look for papers by Bernard Carr, C-A-R-R. And he's the person more than anyone else who has explored primordial black holes and observational constraints on them. Gran Sasso was a remarkable experience for me. The primary reason I accepted your invitation to come here was you promised to take me to the Gran Sasso laboratory, which I had heard about for years, particularly from Barish, who was the leader of LIGO, who really made LIGO a success, and who also was the leader of the macro experiment here in the Gran Sasso laboratory. There are other laboratories, underground laboratories, created more recently, basically patterned after and motivated by the great science being done in the Gran Sasso laboratory. I'm familiar with those, but I had never been to any of them. I'd not been to Snow. I'd not been to the Homestake Mine or the successor to it. And so for me, this was really interesting. What I had not appreciated, because I hadn't really followed details of what was going on here, was how many interesting experiments there are going on. Dark matter experiments of a variety of sorts. Neutrino experiments of a variety of sorts. Double beta decay experiments of a variety of sorts. Things to search for dark matter, put constraints on it if you don't see it, and pin down what it might be. Experiments to study fundamental physics associated with neutrinos. Just the range of things there was really exciting. And also to see and hear the history of how some of these experiments have gone from basically a prototype phase to an intermediate phase to a very mature phase, and very impressive results as you get to the mature phase. So I was looking forward to it. This visit more than, it exceeded my expectations in terms of what I saw there.
Well, thank you very much, Kip. I hope you can be able to come back again to visit us here in L'Aquila. Let's thank
you.
all together Kip Thorne.
Thank you.
E ora, passando per quella porta, quello è un wormhole e vi ritrovate a cena. Incredibile.